Hello, my name is Bob D. Hilster, and I am your particle model guru. Welcome. Today's video is about problem 4 concerning the 5 problems of physics identified by Lee Smolin in his book, The Problem with Physics, or The Trouble with Physics. I've made already 4 different videos on this subject. The 5 problems of physics was the first one was kind of an overview. Then I went into detail on dark matter and dark energy, then on quantum gravity, and my last one was the problem of foundational problems of quantum mechanics. The tuning problem is this. Smolin says that physicists need to explain how the free constants in the standard model of particle physics are chosen in nature. And I had this was in my first video, this slide, and I asked the question, can nature actually choose values of the free constants? I'm not sure his problem is actually even solvable, but we move on. On page 13 of his book, chapter 1, he makes the statement there are about 20 such constants, and the fact that there are that many freely specifiable constants in what is supposed to be a fundamental theory is a tremendous embarrassment. Each one of these free constants represents a basic fact of which we are ignorant. Namely, we don't know the physical reason or mechanism responsible for setting the constant to its observed value, its measured value. I don't know, nature's what nature, it is what it is. And the way we measure it has a lot to do with our instruments and our standards. These values are really set by man, and whether nature has anything to do with values at all is questionable. Well, in the standard model, there are 18 particles. Well, there are a total of 18 particles shown here, but the standard model actually has 12 particles, 4 forces, and a Higgs boson. Gravity or the graviton is not part of the standard model. The effort in quantum gravity is to pull this in and make it part of this, only they're not able to make it fit. And you can watch my video on quantum gravity to get my comments on those efforts. But each of these particles has 3 parameters. There are 3 values, can't read them, and they are mass, charge, and spin. And there are a total of 12 plus there's 16, 17, 18 items here, presumably particles, each of which has 3 parameters that need to be assigned. That's 54 parameters. Not clear at all on how to make it fit with Smolin's 20. One of the interesting points is that these are what mediate the forces between the particles. If you read about them, it turns out the gluon is the nuclear strong force. The photon is assigned the task of the electromagnetic force. Z boson and W boson, they're the weak nuclear force. And so they have particles that have mass, charge, and spin that mediate the forces between the particles. So we're supposed to find out why nature, what's the physical reason for all these numbers exactly the way they are. And as I said, it's us humans that assign the numbers, not nature. Well, I use the same chart on the particle model. When I look at all of these, I only see one particle that could apply, and that's the G1 particle, which originally started out as, when I started on gravity, I called it the graviton. David, my son, warned me not to use that because it has this context to it. So I changed that to just a gravity particle. And then when it came, when I got to the point where I identified that light could be a stream of these G1 particles, and there was G2 gravity, I ended up with the G1 nomenclature. I used that name. And in terms of this chart, you can apply the G1 to the graviton, down here to the electron, and to the photon, although the G1 doesn't replace the photon. I've said that often, it's not quite right. It's a stream of G1s that replace the photon. The N1 doesn't show up here, N1 being a nucleon, which replaces the photon and the neutron. But the other one I find of interest is the neutrino. It's called the electron neutrino. Here I X'd it out, specifically meaning doesn't exist. It was invented to save special relativity. Just ask David. You want to get him to talking about neutrinos? It's one of his prime themes in his dissonant view of current science. So I'm going to talk about this neutrino, which was discovered, so to speak, or invented when experiments were done with beta decay. And this is a chart of beta minus decay, which means that in this decay, an electron is emitted. There is beta plus decay, which emits where a positron is emitted. But I'm going to use the beta minus because it's an electron, and we go from there. Now, this is an example of a nucleus of lithium. Whether this one actually has decay or not, I don't know, but let's use the example anyway. Lithium has an atomic number of 8 and 3 protons, which are shown in red, neutrons in green. And it has a daughter nucleus. After decay, it still has atomic number of 8, but now it has 4 protons. In this diagram, presumably this neutron has morphed into this proton, and when it emits the beta minus particle, which is the electron, when it emits the electron, this neutron changes to a proton, and now instead of lithium, you have beryllium, beta minus decay. What they didn't know about originally was that at the same time, there could have been an electron anti-neutrino emitted, which they claim accounts for the missing energy. Well, nonetheless, the real question is, what causes this to go from here to here? They say it goes from here to here, but they never explain how it goes, except to say the weak nuclear force is the cause of radiation, of weak radiation. It's the cause, even though they say that, they still don't explain how that happens. Okay, in Dr. Carezani's book, Storm in Physics, and this is where David gets his ideas about the neutrino, Dr. Carezani says on page 58 that Ellis and Rooster performed an experiment in 1927, placing a pellet of radium E inside a calorimeter. The calorimeter measures heat by measuring the temperature rise that the radium causes. It heats the water or whatever fluid you have in the calorimeter. The expected value wasn't known until 1930, was calculated then by Pauli, and he calculated as 1.16 million electron volts, presumably using the same calculations that we did during when I described fission, where you convert mass to energy, and you add up when you add up all the masses, you can convert it to energy, and you find out that after beta decay you have a difference. Well, the measured value was only 0.344 measured by Ellis and Worcester, and the difference of that is 0.8 million electron volts. It was a pretty good chunk missing, and we needed something to explain that. Well, in 1930, when Wolfgang Pauli did that calculation, he was attempting to resolve the beta particle energy conundrum by suggesting that in addition to electrons and protons, now he doesn't say neutrons and protons, he says electrons and neutrons. So he's assuming there are electrons in the nucleus. Today we say neutrons and protons in the atomic nuclei. He says it could also contain an extremely light neutral particle, which he called in 1930 the neutron. He suggested the neutron was also emitted during beta decay, thus accounting for the known missing energy or momentum or angular momentum, but it had simply not been observed yet. So small, so tiny, massless, we didn't know about it. A year later, Enrico Fermi named Pauli's neutron the neutrino, which means little particle. So we now have the neutrino, and we have to have it. According to Dr. Carezani, who claims there is no neutrino, that it was artificially invented to save special relativity, he states, normally in science, experimental research starts with when a theory proposes something positive. The neutrino research is reversed. It doesn't start with a theory that says there should be a neutrino and then let's go find it. It starts with a failure of an experiment to give the results calculated, and we need to prove that neutrinos exist, because otherwise special relativity is wrong, and you can't have that. Special relativity has to be right, so we got to find the neutrino, explain the neutrino, and now as special relativity, everything's okay. Well, if you go back to the particles and you look for proton and neutron, they're not there. You don't see a proton and a neutron. In the standard model, that's because the proton and neutron is made up of up quarks and down quarks. Okay, so they don't show up here, but they do describe how how the proton is made up, and it's shown here in this diagram. This on the left, excuse me, is a proton, and it's made up of two up quarks and one down quark. Neutron is made up of two down quarks and one up quark. The up quark has plus 2/3 of an electron, and the down quark has a negative 1/3 of an electron. Explain that? I don't know, but clearly when you add 2/3 and 2/3 to get 4/3 and then subtract 1/3, you get 3/3, which ends up being 1 electron, but it's positive because the up quarks are positive. The 1 is positive, so the proton has a positive charge. Isn't that amazing? The neutron has two down quarks, which has a negative value, and you add these three up and they come up with 0, and the neutron has 0 charge. You just sum up the charges and you can find with the electronic charge of the proton, neutron, or whatever particle is made up of up and down quarks. Aren't we scientists clever? So in beta minus decay, the neutron, this particle over here, morphs to a proton over here and emits an electron in the process. But there's no electron here. Pauli said electrons and what, protons? No, there's no electrons. So how does it emit an electron if there aren't any? Well, the particle model, Adam, I'm going to go into a little bit of a discussion about this because it explains the reason why I make the assumption. This is an assumption. I can't prove this. There's no evidence, direct or indirect evidence, that this should be true. But I have my reasons for suggesting it, and including beta decay as well. But in the gravity 2, which holds the nucleus together, or the nucleon, which keeps the G1 in orbit around the nucleon. If you have one N1 and one G1, you have hydrogen. So the hydrogen atom has more than 8 G1 particles. So you have to imagine there's more like 2,000. Regardless, the G1 must have open space in order that the G2 passes through the G1 and the nucleon. It has to pass through. The way gravity works, it has 3 interactions, which I've talked about before. The particle can pass straight through and not do anything. It can, as it passes through, it can hit and push this one, or it can pass through here and hit and push that one. And in that context, you can establish a G2 gravitational force. The blue arrows around the atom holding the nucleon together and keeping the G1 in orbit. G1 must have open space. And G1s hit and push each other when they're hitting another G1. For example, here's the G1, which is a red arrow represents only one part of the Newtonian type gravity, G1 gravity, but let's assume that this is coming at the atom, but if it comes and hits the G1, like particles are not going to pass through each other. They're going to hit and bounce off, and if you hit hard enough, they might annihilate each other, blow each other apart, whatever. So it's going to hit and bounce off the G1. Like particles do not pass through each other. As similarly, if the nucleus is made up, the nucleon is made up of G1 particles, the G1 gravity, when it hits the nucleon, is going to hit, bounce off, and push the atom. G1s hit and push when hitting another G1. So if this is made up of G1s, then we have the interaction we need. Well, these things are clumped together, and I contend that G1s in space can be combined. If you get 2 G1s moving in about the same direction, coming closer and closer in space, eventually G2 gravity is going to cause them to stick together, just like they are in the N1 particle. Well, it's possible, although it doesn't seem likely, but it's possible that as G1 particles are going through space, more and more get clumped together until you could get a nucleon in space. And if a G1 particle passes by this nucleon that's in space, and it's at the right direction, the right velocity, it can orbit, because there's a G2 field out there, and you could actually make a hydrogen atom in space. So they can be combined. The final reason that I think G1s the nucleon is made up of G1s is beta decay. There is a G1 in the nucleon. It's available there to be emitted. When you have up quarks and down quarks, unless they're made up of electrons, which I doubt because the electron's on the same chart with the up and down quark, they're separate particles. The proton, neutron don't have an electron in them, but in the particle model, our nucleon, I'm suggesting, is made up of G1s, and hence there is a source of a G1 particle available to cause a beta decay. Okay, so let's assume that we have a nucleon, N1 particle. This is the whole thing is an N1 particle, and it contains, well, maybe more like 2,000 G1 particles, because the nucleons and protons are very large compared to the G1. Well, there's lots of them there, but I maintain for a stable N1, you have a balance, a distributional balance. All the G2 forces on these outer G1s are the same. G2 force on that inner one are equal and opposite. The net force is 0. And if a bigger one with 2,000, if it's balanced in some way, you'll get a stable nucleon. If you have extra ones that happen to get stuck that don't belong there, then you have an unbalanced distribution. And the forces on these particles now are not the same. The force on the center particle is no longer balanced and equal. It's unbalanced. So this is unbalanced, and it also, I guess, depends on how much unbalanced. And I'm speaking qualitatively, not quantitatively, I don't know, but I'm suggesting that radium E, for example, has an unbalanced nucleus. So what happens in beta minus decay in the particle model? You have a nucleus, a nucleon, an N1 particle that has an extra G1 particle. There is a unbalanced forces inside here. These are not equal and opposite, so you're getting forces in different ways on different particles that are not balanced. The second thing you have is that G1 force field around it isn't always perfectly balanced. We talk about it being perfectly balanced in order to give a simple, nice, neat explanation, but the real world isn't that way. The real world, there are objects around the outside of this that's constantly changing. The G2 force field is not static, is not constant, it's changing. How much it's changing, again, I can't say quantitatively, but qualitatively, you know you've got things changing around you. You know that the force field around it can change. And when this is unbalanced and you have enough of a changing force, it is possible for G2 gravity to push the G1 particle out and emit a beta minus particle. The particle is available. It doesn't just have up and down quarks, it has G1s, and the G2 force pushes it out. And by the way, it must reach escape velocity. Just like the spaceship on Earth, you got to push it hard enough. And the G2 force moving at faster than light, I estimate approximately the speed of c squared, and pushing on the G1 has enough force if it gets unbalanced enough to push it out, cause beta decay. Well, what about the nuclear force? I have never suggested that the particle model has a I haven't found one. Found gravity 2, and we've known about gravity 1, Newtonian force, for a long time. I have not found a weak force. There does not exist in the particle model. Only There's only gravity 2, which is a nuclear strong force. There is no nuclear weak force. The nuclear weak force is just the nuclear strong force being imposed on a nucleon that's unbalanced, being surrounded by a gravity 2 field that's not static, and decay happens. And this is what causes what is called weak radiation, but it's the nuclear strong force in an environment that is not stable. Excuse me. What about the missing energy? Well, until there's a standard for the N1 and G2 particles using a value of G2 mass, I can give no quantitative answer. I've been, unfortunately, using this excuse long enough. I'm about ready to at least make a suggestion. And secondly, is E equal mc squared the way to convert mass to energy? Well, if you use the right mass, maybe it is. But when you use kilograms for the value mass of the neutron and the electron, I contend you can't guarantee you have the right answer. Can the particle model equations? Yes, I have equations. I have used them for gravity and made calculations. Can they be used to do the needed calculations for beta decay? Don't know. The TBM has a workable model. I just explained the workable model for beta decay, but the calculants have to wait until I get the standard. Sorry, I know it sounds like an excuse, but it's the point I'm at in the development of the particle model. My name is Bob D. Hilster, and I am your particle model guru. Tune in next time when I'll explain more of the universe using the particle model. Thank you for your attention.